Now that we've created the connector section, we need to assign it to the connector wires we created before. So expand out the assembly item in the model tree and double-click on Connector Assignments. Abaqus prompts you to select the wires or attachment lines to be assigned the section. Now in our case, we'd gone ahead and created a set of all the connector wires, and this is why we did it, so that it would be easier for us to select those wires at this step. So we're going to click on the Sets button, and in the region selection window, we'll click on Set of Connector Wires. If you like, you can check off Highlight Selection and Viewport so you can see them better. And once you're satisfied, click on Continue. Next, Abaqus wants you to select the section that you wish to assign to these wires. Since we've only created the one section, it's the only one available in the drop-down list, so select it and click OK. So now we've created pin joints at most of the nodes where the cross-bracing connects to the frames. For the remaining nodes, we're going to use equation constraints. In order to do this, it's going to help if we assign those nodes on the cross members as well as the frame to sets, so it's easier to select the one we want. Expand out the instances container in the assembly container. Right-click on frame 1 and choose suppress. This suppresses the frame 1 instance, and you only see the cross-bracing now. Now it's going to be easier for us to select the nodes on the cross members and assign them to sets. Double-click on the sets item. We're going to call our first set cross node 1 and select it from the viewport. Repeat the procedure for cross node 2. Now let's unsuppress the frame and suppress the cross-bracing. Now you see only the frames. Let's create frame node 1 and frame node 2. Remember to unsuppress the cross-bracing once you're done. Now that we've created the sets, let's add constraints. Double-click the constraints item in the model tree. Now we're going to use equation constraints, so let's talk about how these work. You basically write out the constraints in the form of an equation that looks like a1 u1 plus a2 u2 plus a3 u3 and so on equals 0, where a1, a2, a3, basically all the a's, are coefficients, and all the u's are displacements of specific nodes. So for example, to constrain cross node 1 and frame node 1 in the x direction, we're going to say 1 times the displacement of cross node 1 in the x direction minus 1 times the displacement of frame node 1 in the x direction equals 0. And that would constrain the node in the x direction. We'd repeat the procedure for the y and z nodes, and then we'd repeat the entire thing for cross node 2 and frame node 2. So basically in the end you should have 6 equations. In the Create Constraint window, let's set the name to Join Constraint 1 and choose Equation from the type. Click Continue. In the Edit Constraint window, our first coefficient, or A1, is 1, and the set name is crossNode 1. And this equation is dealing with constraints in the x direction, so we're going to set the DOF, or degree of freedom, to 1. We're going to set A2 to -1, and the set to frame node 1 with the same degree of freedom, because that's also for the equation in the x direction. So what this represents is 1 times the displacement of the set cross node 1 in the x direction minus 1 times the displacement of the set frame node 1 in the x direction should equal 0. Or put in simpler terms, the displacement of cross node 1 equals the displacement of frame node 1 in the x direction. We'll repeat the procedure for the y direction. We'll call it join constraint 2, and this time we'll set DOF to 2, indicating it's for the equation in the y direction. And then repeat the procedure for the z direction. We then create the equation constraints for the other node, which is cross node 2 and frame node 2, in the x, y, and z directions. So in the end, you should have joint constraints 1 through 6. Now that all the joints have been created, let's move on to the steps. We're going to create a step called apply loads, which is a static general step, and insert it after the initial step. Now let's create the load. Double-click the loads item in the model tree. We're going to call it crossLoad1. It's going to act in the apply load step. It's a mechanical load, and it's of type line load. Now line load basically makes a force per unit length act on a beam. Abaqus still thinks you're selecting sets, so click on Select in Viewport to allow yourself to select the beam member in the viewport. Select the beam member and apply a load of 1000 newtons in the negative y direction. Similarly, apply loads for the other 3 beam members. Let's create the boundary conditions. Double-click the BC's item. We're going to call it fix bottom and apply it in the initial step. For the type, choose displacement/rotation. For the region, select all the beam members at the bottom of the structure. We're going to check off U1, U2, and U3 so the beams at the bottom of the structure cannot translate in any direction. However, they're free to rotate about any axis. You might have noticed that we did not apply equation constraints to two of the nodes at the bottom. We only used the equation constraints for the two nodes at the top of the structure, because if we'd used equation constraints at the bottom and then used the boundary conditions we just did, we would have basically over-constrained the structure, and this would have given us an error. Now let's mesh the structure. We'll start by meshing the cross-bracing. We'll assign it an element type B31, which is a two-node linear beam in space. And we'll seed the edges by number, assigning 4 elements to each beam of the cross-bracing. We'll do the same thing for the frame. Now that the parts are meshed, let's create the job and run it. There appears to be an error. It reads, the following connector assignments reference regions which are empty, or have been deleted or suppressed. So it's possible we've deleted or suppressed something we earlier created by mistake. It refers to section assignments to the frame cross-connector section. So let's take a look in the assembly container. Maybe it's in the sets item or in the features item. And here we see it. It looks like this feature has been suppressed, either by a mistake on my part or at some point during the setup, Abaqus for some reason decided to suppress it. But we're just going to unsuppress it and continue on with our analysis. Once the analysis finishes running, we can right-click on the job and choose results. And I'm going to plot the deformed shape just to make sure the analysis did actually run as expected. Of course, there's no way the frame's going to deform to the extent you see in the viewport. Abaqus has gone ahead and multiplied the deflection by some factor to make it more visible to someone looking at this. But if you went into the common options and changed the scale factor to 1, you probably wouldn't be able to see any deflection at all. This tutorial's been pretty heavy on other content, so we're not going to spend any time post-processing. Hopefully you've got a good idea of how you analyze beam structures, and you've also learned a thing or two about connectors and equation constraints.